Hello and welcome to the second lesson of the computational thinking unit of computer science. Last lesson we looked at decomposition. This lesson it's abstraction. We'll start with a similar starter to last time. Which of these four definitions do you think is the correct one for abstraction? Now bear in mind, last lesson we looked at decomposition. These are the same definitions, so one of those is already taken. Then after that, have a think about what abstract art is. What is it about abstract art that makes it abstract? That might help you choose the correct definition. So pick one of those. Okay, hopefully you've chosen one of these. Let's see if you were right. Abstract art is art where it isn't an accurate representation of the subject. It's got a lot of details missing, but it has enough detail that you can tell what it's meant to be. In computing, it's a similar story. So abstraction is removing unnecessary detail from a problem in order to simplify it. It gives us a much clearer idea of the problem we're trying to solve if we've gotten rid of all the excess details, of all the stuff that doesn't matter. We don't want the problem clouded with things we don't need, so being able to take out the bits that are unnecessary can save us a lot of time. We'll look at an example in a minute, but first let's make a couple of notes. Abstraction is the act of removing unnecessary detail from a problem to simplify it. Could you make sure that's written down wherever it is you're making your notes? Okay, let's have a look at an example. So this will give you an indication of how we naturally abstract quite a lot when we solve problems by ourselves. We're going to formalize this, we're going to look at how we can make it a lot better, but this is something you would probably do automatically. Have a go at this if you like. If I was to give you this task, draw me a picture of Bob and Sally. The picture must show that Bob is roughly twice the height of Sally. Now if I only gave you 10 seconds to do it, and you had a drawing of it, it would probably end up something like this. That's enough to show us what we need to. Now bear in mind, they don't look like Bob and Sally. They don't look like humans. Humans don't have perfectly circular, round heads. They don't have stick-thin features. But that's enough for us to identify that those are two people, and crucially, that Bob is roughly twice the height of Sally, which was the thing we were trying to get across. We might take it a bit further. We might say instead, draw me a picture of Bob and Sally. Bob has blonde hair and Sally has brown. Bob is twice the height of Sally. Well, we could just add something like this. Again, not an accurate representation, but it's enough there that we can get the information in the problem across. There's actually another layer of abstraction going on here. Bob's hair is not blonde, it's yellow. But in the context of hair, we accept that yellow means blonde. It doesn't have to be accurate. It has to be enough to get across the information we're trying to get across. By abstracting Bob and Sally, we saved everyone a lot of time. We saved ourselves a lot of time creating the picture. We didn't have to get out the pastels and draw a photorealistic image. Just stick figures would do. We saved the person viewing it a lot of time, because they weren't distracted by all the detail in there. They could just look at it and say, ah, there's two people, Bob's tall, Sally's short. They saw that straight away. And not distracting the end user with excess information is a really important thing. We can see that even more in our second example, which is the London Tube map. Now the London Underground is a very complex network of 250 miles of underground train tunnels. In 1931, Henry Beck was tasked with creating a map of the network that enabled passengers to plot their route between different stations. He used some very clever abstraction in order to make the map really easy to use. Now, down here are a series of characteristics of the underground. I want you to decide which of these are important for the map and which ones we can disregard. So, the geographical location of the stations. Do we need that information to make an underground map, or can we just ignore that and plot them anywhere? The route each train line takes, so the pattern it takes, do we need to know that? Or can we just disregard that and draw it as a straight line? The distance between the stations, which train lines connect the station together, the depth of each station underground, the speed of the trains, the year each train line was completed. There's lots of information about each of those. Which of them do we actually need? Have a think about it for 30 seconds, and then we'll have a look at what Henry Beck did. Well, for a map, Henry Beck took quite an impressive decision. He decided almost none of this was relevant. It didn't matter where the stations actually were. It didn't matter what route it took. It didn't matter how much distance there was between the stations. All that mattered was this one here, that which train lines connected which stations together. Because if you're planning a route, it doesn't matter how long the line is, it doesn't matter which route it goes. All that matters is, can I get from this station to this station, and then from here, can I get to this station? So what he came up with was one of the most iconic maps in the world. It was the London Underground map. This one, if you were to compare it to an actual geographical map like this, you can see how the tube map is so much easier to work with. The locations of the stations on this map are not accurate, not even close. It doesn't matter, because if I'm at this station here and I want to find a way to get to this station here, I just need to see which train I need to get on and which station I need to get off at to get on another train. As long as I can read that, I don't need to know anything else, and it resulted in a much better map than if he'd gone with geographically accurate. Now, in computer science, abstraction takes many forms. One of those is called abstraction by generalization. In generalization, it's still a form of abstraction, which is where we make a model of something. And in the model, we model only the important aspects of the problem. Like in any other abstraction, we get rid of unnecessary details. In order to do that, we look for something called general characteristics. A general characteristic is one that applies to a broad category, not a specific example. That's easier to understand if we look at some actual examples of this. So if we've got a cat, say our cat here is named Tibbles. That's a specific detail of our cat. The broad case would be to say cats have names, or a cat has a name. If we were making a model of a cat, it would have a name. We don't care what that name is, that can be decided later, but knowing that a name is a category of it, that's a general characteristic. This ball is green is a specific characteristic, but just to say a ball has a colour is a general characteristic. So if we are making a model of something in computer science, we tend to make a model of the general case. We make a ball that can be assigned a colour. We don't make a specific ball that is blue. We make a ball that has a colour. We make a cat that can be assigned a name. There's a lot more about this on the BBC bite-sized page that's linked on the VLE. So the next 10-15 minutes, I'd like you to have a look along that page. Most of it is very similar to stuff I've just talked about, but it goes into it in more detail, and again from a different perspective that some of you might find easier. It also, on the last page, has a link to a quiz which I'd like you to have a go at. That will just help you practice for the quiz that you're going to do for the assess task. So read through the BBC bite-sized page that's linked on the VLE and have a go at the quiz. Pause the video here, and then in about 50 minutes time when you're done, you can resume it and carry on with the lesson. Okay, so if you've done that quiz and you've had your practice, you should now find it relatively easy to do the quiz on the VLE. Now bear in mind, like last time, this is not a checkpoint. You are allowed to use things to help you with this quiz. You can use this PowerPoint, you can use your notes, you can look things up on the Bite Size website, whatever you need to. So if you get to a question and you don't know how to answer it, look up the answer, don't just guess and move on. Getting a low score in this is not going to be acceptable. You need to look up the answers and get a good score in it. When you've done this, if there's still time left over that you need to fill, there's another task you can attempt. We're going to use Abstraction to produce a map of the college for parents on open day. Now, similar to the London Underground map, we're going to be careful not to get bogged down in detail. Parents need to know how to get from one classroom to another. They don't need to know the geographical accuracy of it. They don't need to know the size of the classrooms. It doesn't need to be drawn to scale. I want you to draw the easiest to follow map that you can come up with that would allow a parent to look at it and go, okay, I'm here. In order to get to here, I need to go this way and work their way through it. Okay? So if you've done that, you can upload that to VLE. This is the extension. The main thing you have to do is complete the quiz. Okay? Do the best you can, and I'll see you for next week's lesson.